It's my great pleasure to congratulate our 2022 Physical Sciences and Engineering Laureates. Professor Matt Brookes. Professor Matt Brookes is unable to be here this evening due to certain pesky virus.
Good evening, everyone. I was very much looking forward to spending what I'm sure will be a wonderful evening with you all. However, unfortunately, COVID had other plans. So, massive apologies for my enforced absence. Nevertheless, I would like for the next few minutes to tell you a little bit about the research that our group here in Nottingham works on. So, like Madeline, my research focuses on the human brain, which is one of the most complex and remarkable systems on the planet. In the outer surface of the brain alone, which is called the cortex, there are around 86 billion electrical cells called neurons. Each one of those neurons is connected to about 10,000 other neurons, and this forms a network that controls everything we see, everything we feel, the way we move, all the way to our emotions and our personalities. Now, obviously with such a complex system, there are lots of things that can go wrong, and disorders range from neurological conditions like epilepsy or dementia to severe mental health problems like schizophrenia or depression. We still understand relatively little about these, and so human brain health is, I think, one of the biggest challenges for 21st century science. So, why is a physicist standing here talking about brains? Well, it turns out that a lot of the technologies that we have to probe the brain come directly from physics. For example, magnetic resonance imaging, or MRI, which you can see here, provides images of brain structure with exquisite detail, and that's really useful if you're looking for a structural abnormality like a tumour or a lesion. Unfortunately though, with a lot of brain disorders, brain structure looks pretty normal. There are no lumps or bumps. It's actually the activity within that huge network of neurons which goes wrong. This means that rather than imaging structure, we need to start to think about new ways to image brain function. So I work with a technique called Magnetoencephalography, or MEG, and to explain how it works, let's go back to the neuron. Neurons are electrical cells. So when the network is active, we get electrical current flowing along these cells, which is shown here by the red lines. Now, like all electrical currents, these neuronal currents generate magnetic fields, which are seen here as the white circles. These tiny fields from thousands of neurons add together, so when we look at the whole brain, we see fields generated by active areas of cortex. Those magnetic fields pass straight through the skull and they exist outside the head, so we can detect them, and in this way we can get information about electrical brain function. So here's a traditional Meg Scanner. A subject sits with their head in a helmet, and inside there are lots of magnetic field detectors placed around the head. When we run a scan, we get maps of magnetic field across the head, seen here in red and blue. Now those fields aren't particularly useful on their own, but we can apply a whole bunch of mathematical trickery which turn those fields into 3D images of current. So here the yellow areas, so regions where the brain network was active when we undertake a task. We can even go one step further, and we can measure dynamics. In other words, how neural currents change millisecond to millisecond. So here we see currents in the brain change as a person feels braille characters with their index finger. So each time they feel a pattern, you can see the brain respond. So MEG is a powerful technique to measure brain function, but there's a problem. The system is massive, you have to put your head inside this helmet, a scan takes a long time, and you can't move more than about 5 millimeters. And that makes the Meg environment intolerable for lots of people, especially children. The system is also built for adults, and it's one size fits all, which means that if you put a baby in there, their head is so small and their brain is just too far from the sensors to measure anything meaningful. So going back around 5 years, our vision was to change what a Meg scanner looks like to something like this. A hat that you can pull onto your head. The sensors would move with the head, so you could move freely during a scan. The hat would adapt to different head sizes, so if you were scanning a baby or an adult, you just use a different size. The sensors would be really close to the head, so we get better data. Now, 5 years or so ago, that was really a dream, because the fields from the brain are absolutely tiny, and the only sensors that were good enough to detect them had to be operated at extremely low temperature, which is why conventional Meg systems are so big. However, for a few years we've been following the development of a new type of sensor called an optically pumped magnetometer, or OPM. OPMs don't require low temperatures, and by 2015 a miniaturized sensor had emerged. So this is the first generation OPM. It's still quite big, it's about 10 centimeters long, but we worked with our collaborators in the USA to develop a second generation OPM, which is about the same size as a Lego brick. And it's these tiny little sensors which have changed fundamentally the face of MEG. So how does it work? So inside every sensor, we've got a laser on the right hand side and a photodetector on the left, and in the middle there's a glass cell that's full of atoms, shown here as the green dots. These atoms all belong to a chemical element known as rubidium. Because of a property called spin, each atom behaves like a tiny little magnet, generating a tiny magnetic field of its own. The direction of the magnetic moment is shown here by the black arrows. So when nothing's happening, the atoms have randomly oriented magnetic fields, so they all point in different directions. But quantum mechanics tells us that we can talk to these atoms via the laser. When we turn the laser on, if the frequency of our laser light is just right, those atoms, the black arrows suddenly align in the same direction, pointing along the path of the laser beam. Quantum mechanically, we say that the atoms have absorbed photons of the laser light and they're all pumped into the same quantum state. Once they're all aligned, the atoms can't absorb photons anymore, and so the gas is transparent to the laser. So the laser passes all the way through to the detector without interacting with the atoms, and the power of the light at the detector is maximum. But if we bring our OPM close to the brain, which is a source of magnetic field, this magnetic field travels through the cell. The direction of the magnetized gas starts to swing away from the beam of light. The atoms are no longer aligned, so they can start to absorb photons again. Because photons are absorbed, the detector will see less light. Mathematically, we can model this process using something called the Bloch equations, and we can work backwards and use the decrease in light to tell us how strong the magnetic field from the brain was. It's about 5 years since we started using OPMs. In 2016, we ran simulations to see what might happen if we could deploy OPMs for Meg. By 2017, we'd got one single OPM and we were able to see the magnetic fields from the motor cortex when someone moved their fingers. By 2018, we'd managed to integrate 13 OPMs and develop what would ultimately become the first prototype system. We worked on some of the first pediatric measurements, we paired our system with virtual reality, and by the end of 2019 we'd developed the smaller sensors. And by 2021 we had a second prototype with 64 OPMs, which could cover the whole brain. So with this system, for the first time, We could image electrical brain function with millimetre precision, not when somebody's lying still in a scanner, but when they're in a natural environment, moving around, doing normal things. This is actually quite an old result, but it's significant because it was the first time that we saw that it was possible to measure brain activity whilst a person moved. So you can see the motor cortex firing up when a person starts to play the game. And of course now we're taking this further, measuring brain function as a person moves around a room. The point here really isn't that you can measure brain activity during a game of table tennis, but rather if you can make the system work whilst a person moves, you can do fundamentally new things, like image a baby who won't keep still, or a child having an epileptic seizure, or an elderly person with Parkinson's disease. So it begins to open up fundamentally new possibilities that are unthinkable with conventional scanners. One thing that we're really excited about is new ways to measure brain connectivity. In other words, how different parts of your brain talk to one another through our networks of neurons. So here, the blue dots show active regions of the brain, and the pink lines represent connections between those regions that are made when we undertake a task. Why is that important? Well, brain communication breaks down in a lot of disorders. One really topical example is here, concussion, which has long-lived effects in lots of people, yet MRI scans are often normal. Using Meg and measurements of connectivity, we can start to see the effects of concussion. For example, this network of regions in blue has had its level of connectivity diminished in patients who had suffered a bang on the head. Perhaps most excitingly, we can now measure brain activity in children. And we can start to understand disorders that affect the brain in the early years. Again, this opens new possibilities, but we're not child psychologists, and we as a research team can't fully realise this potential. It was for that reason that last year we founded a company to make our scanner available to researchers and clinicians around the world. It's still early days, but our products are already being used in lots of places, children's hospitals like Great Ormond Street here in London looking at epilepsy, the Sick Kids Hospital in Toronto, Canada looking at autism, the US National Institute of Health have some of our stuff, as do the China National Academy of Science, hospitals in Brussels and Amsterdam. I think having people around the world work with our technology is probably one of the most exciting things that we've done. So that's where we are. We have a new technology which can image brain activity with higher sensitivity and better spatial resolution than the current state of the art. It can adapt to children, it allows patients to move freely, and it's even lower cost. And all of that made possible by understanding the fundamental quantum mechanics of an atom. I would like to take this opportunity to express my sincere thanks to Sir Leonard, the Blavatnik Family Foundation and the New York Academy of Science for this truly amazing honour. All of the work that you've seen has been made possible not just by me, but by a group of incredibly talented scientists, and I'd like to thank them, in particular my colleagues in Nottingham, and our many collaborators all across the world, particularly those at UCL here in London and at QSpin in Colorado in the USA. Obviously, I'd like to thank our funders, in particular EPSRC and Wellcome, and the University of Nottingham for their ongoing support for this research programme. I think as scientists, we're all inspired by someone, and the defining influence on my career was my PhD supervisor, Peter Morris. Peter set me on this path many years ago and instilled a passion for science, which I think is something I'll always be grateful for. And finally, a massive thank you to my family, my parents, my grandparents, my two amazing children, and last but not least, my wife. Once again, apologies for my enforced absence, my congratulations to all of the laureates and finalists, and I wish you all an absolutely wonderful evening. Thank you.